the webinar, a little bit of background of the theory that's behind the webinar, the Energy Institute methodology, explaining it, the Energy Institute guideline stage approach. Then we'll be working with the AFT Excel spreadsheet to calculate the LFF. We'll be working in example, and then we'll have the conclusions and then the questions and answer session. So overview. This webinar provides a guidance on how to use AFT 10 new solar thumb power level calculation. We'll be following the procedure of the Energy Institute, which was created to help minimize the risk of vibration fatigue of process piping. We will apply the procedure using acoustic induced vibration, AIV, as the source of excitation. Energy Institute covers three forms of source of excitation: FIV, flow induced vibration; FIP, flow induced pulsation; and AIV, acoustic induced vibration. As I said, in this webinar, we'll be covering AIV, acoustic induced vibration. So a little bit of background, what's behind it? High frequency acoustic excitation, AIV. That is how it's normally called in the industry sector, AIV. In a gas system, high level of acoustical energy can be generated by a pressure reducing device, such as a relief valve, control valve, and orifice plate. Acoustical fatigue is a concern as it tends to affect security-related systems, such as relief and blowdown systems. This form of excitation can generate severe high-frequency vibration on the pipe wall. The vibration takes the form of local pipe wall flexure, resulting in potentially high dynamic stresses levels at the circumferential discontinuity of the pipe wall, such as branch connection, welded pipe support, etc. What makes this excitation most critical is that the failure can occur in a short period of time, even in few minutes. So if you discharge in a system that has acoustical induced vibration and you have a connection or a welded support, it can fail during the operation. It doesn't have to take long for it to fail. Energy Institute methodology that we'll be using here. It is described in the document titled Guidelines for the Avoidance of Vibration-Induced Fatigue Failure in Process Pipe Work. The document is based on the Outcome Joint Industry Project, which was initiated in response to a growing number of failures in process piping. This methodology intends to help minimize the risk of vibration-induced fatigue of process piping. These guidelines use an evaluation method for the vibration failure possibility based on the likelihood of failure, which is called LOF index. Energy Institute guidelines provide a stage approach. The initial stage is a quality assessment, which is undertaken in order to identify the potential excitation mechanism that may exist. You can have more than one. Provide a means of risk ranking of process system. It gives an overall risk qualification of high, medium, and low after you do the quality assessment of the system. Where an excitation qualification results in high or medium score, the corresponding excitation mechanism should be subjected to a quantity assessment, which is the second stage of the methodology. So second, a quantity assessment is undertaken in order to be applied for each excitation mechanism identified from the quality assessment as high or medium risk. This results in an LOF, likelihood of failure score, for each discontinuity in the main line. Third, Energy Institute guidelines provide detail of on-site inspection and measurements techniques to help refine the quantity assessment. And fourth, Energy Institute guidelines also provide some corrective action guidance to reduce the risk of failure to an acceptable level. So here is the LOF calculation. First, we calculate the sound power level, sound power level at the source. Then we ask the question whether it's higher than 55 decibels or not. In case no, the answer is no. The LOF will be equal to 0.29. And in case yes, we continue calculating the LOF. We calculate it for each discontinuity, and it applies to flow chart that will be shown now. So now we continue calculating the LOF. We apply the stress concentration factor on the type of discontinuity, depending on what you have, if it's well-loaded type of fitting or not, if it's duplex or not. And finally, we calculate the LOF for each discontinuity. Using AFT spreadsheet to calculate the LOF. Spreadsheet is provided upon request for AFT customers current in the SUM. So if you have a Fathom or Arrow and you want to receive the spreadsheet, just send us an email, and if you're current on SUM, we'll provide it for free. This spreadsheet comes with an instruction manual with a detailed explanation for each type of vibration source. The spreadsheet has a tab for each type of vibration source. We have FIV calculation for liquids, calculation for gases, FIP, flow-induced pulsation calculation, and AIV, which is the one we'll be using in the webinar. In each tab, it is indicated in color. The user input, what you have to input in your spreadsheet. What will be imported from AFT software. LOF calculation results. So I'm going to open to show you the spreadsheet that you'll be receiving. It's called flow-induced vibration calculations. So here you have the different tab, FIV, flow-induced calculation for liquid, for gases, for induced pulsation, and AIV, which is the one we'll be using. In pink, you see is the user input. So this is the information you have to provide. You have to input to the spreadsheet. This is the one we're going to import from, in this case, Arrow, because you're using AIV, and the results is calculated. Like in this case, the LOF calculated is 0.63. It's the most critical one. Also, there's a manual that, as I said, explains in detail, step by step, how to use the spreadsheet, flow-induced vibration, and so on. So we're going to use it in an example. We have a system that transfers steam from tank J1 to tank J6. We have a quarter of an inch downstream orifice, and we want to know if it's at risk of failure of AIV. So first we do the quality assessment, the first stage of the Engineering Institute methodology. And we ask the question, 3 questions. Is choked flow possibly, or are sonic flow velocities likely to be encountered? This question is taken directly from the document, which is the question we ask for gas systems in the quality assessment. Then we ask another question: how many possible sources of vibration are present? Because the discontinuities can be effective for more than one source of vibration. How many discontinuities are present? Because we have to calculate the LOF as many discontinuities as we have in the system. So the results. It tells from the model, we get that sonic choking is occurring. It's occurring in the junction J3, the expansion. It's also occurring on the orifice, and it's also occurring at the tank. So I'll bring Arrow. Here's the model. We run it. Say OK. Go to the output. We go to the sonic choking, and here's the it's telling us the sonic choking is occurring. Conclusions of the quality assessment. First, the first question, is sonic choking occurring? Yes, sonic choking is happening. As we saw, it's happening at 3 points. Excitation qualification is high because sonic choking is occurring. It requires a quantity assessment, which is the second stage of the methodology. How many possible sources of vibration are present? Well, upstream the discontinuity, we have 2 possible, 2 upstream the pipe connection. How many discontinuities are present? We only have 1. So now we go to apply the quantity assessment. It's the second stage of the Energy Institute methodology. To do that, we first run the Arrow model. We check the noise level at the junctions where sonic chokiness are happening. If the noise level is below 155, we don't have to proceed further. The LOF is equal to 0.29, so we no need to calculate the LOF because according to the manual, it's already 0.29. If it's higher than 155, we proceed to calculate the LOF using the AFT Excel spreadsheet. So now, what are the results? We have a noise level of 180. We have a noise level of 162, which means the noise level is higher than 155 decibels. And now Arrow will give us a message saying, following junctions have a predicted sound power level greater than 155. The Energy Institute guidelines for avoidance of pipe failure, second edition, indicates that this increases the likelihood of failure due to high frequency acoustic excitation in junction J3 and J5. So now you have the warning. that is indicated. So I'm going to bring the software. We look at the warning, and here's the warning indicated us that the sound level is above 125. We also see it here at the sound power level at the junctions. We have 162 and 180. And also we can see it in the new feature in our software, which is the layers. We created a layer with sound level, and we see it here. The sound level is above 155, 162. So now we have to proceed to calculate the LOF for this pressure gauge connection and to see whether or not it will fail according to the methodology, Energy Institute methodology. So, as I said, we proceed to calculate the LOF using the AFT Excel spreadsheet. Quantity assessment now. We open the AFT Excel spreadsheet. Save it with another name. We don't want to ruin, we want to save the AFT Excel spreadsheet that you received. So if you make a mistake or something, you don't want to, you want to be able to go back to it. So save it with another name in order to protect the original one. We select the tab for the source of vibration. In this case, we're selecting AIV, acoustic induced vibration, because that is what we're evaluating. Fill the required user input information in the spreadsheet. And here are what you have to fill and the inputs. NW stands for molecular weight, and so on. So we open the spreadsheet. We come here. As you can see, I saved it with another name. AIV calculations, another name for it. I selected the tab for acoustic induced vibration. So now we fill the user input information, the molecular weight. It asks if there's sonic choking or not. It tells the vibration sources. We say it's junction 3 and 5, and so on. We fill the pink information that is required by the spreadsheet. So now we proceed, once we fill the the user input information, we open the model. We open the Excel Export Manager, and we create Excel export sheet following the instruction manual. We have two sources of vibration. So for the first source, we have to create the following Excel export sheet for the first source. So we have the first source is the orifice. We have to export to the spreadsheet the pressure in stagnation inlet. It has to be in the same units that's indicated in the manual. Pressure in stagnation outlet is Pascal. In the pipe connected to the pressure reducing device, we have to input, send the temperature, static outlet, and the mass flow rate from the orifice. Then we go to the second source of vibration. We have to send the same information, but in this case, if the area change, the same. Stagnation inlet, stagnation outlet, temperature, that's a pipe connected to it, and the mass flow rate. And finally, since we have one discontinuity, we only send the information to the spreadsheet is the diameter hydraulic. We export the spreadsheet. So I'm going to bring the model. Here we have the Excel Sport Manager. We open it, and here is the table that I described in the presentation. The first four would be for the first source of vibration, which is the orifice that is immediately connect the source of vibration that is closer to the pipe connection pipe, the discontinuity, which is the pressure gauge. From the 4th to the 8th, it's the same, but the second source of vibration, which would be J3, where sonic choking is also occurring. If sonic choking were not occurring here, you wouldn't mention it as a source of vibration. And finally, the pipe 5, which is the pipe connected to the discontinuity to evaluate the discontinuity in the system. Then, as I said, we hit Sport now. And we view the LOF results in the spreadsheet. Use the guidelines to determine the appropriate action based on the LOF. So we come here. Arrow imported all the blues, okay? Pressure, temperature, and mass flow rate. Here it is. And we get a main LOF of 1.0. Here's the results that I showed you, just showed you. LOF is equal to 1, which tells us that failure is likely to happen, which means corrections need to be applied for the connection you have. Okay, so that is a result of the evaluation of the Engineering Institute for the acoustic and doom vibration. There's a possibility of failure, so we have to apply the corrections. So now, what do we do? Well, as I said, Engineering Institute methodology has recommendations. It tells us if LOF is equal or higher than 1, corrective actions shall be examined and applied as necessary. And it indicates it in paragraph TM-10. So let's see what recommendations they have for the possibility or to reduce the risk of failure due to acoustic induced vibration. The T10.7 high frequency excitation has a recommendation. You can take actions in the mainline excitation, reduce the in-mass flow rate. That's the first recommendation. Change the valve trim in order to reduce, if it's in the case it's a valve. In our case, we have an orifice and area change, so it wouldn't apply this. But if you have a valve trim that is creating a noise like a relief valve, changing the trim might solve the problem because it reduces pressure drop, the drastic pressure drop, and it might correct the problem of sonic choking. Also, changing length, actuation in the with distance. So you can, in the one of the possible solution is right here. It's connected to 5 feet. So you might say, okay, I'm not going to connect it at 5 feet. I'm going to connect it 10 feet or further down to, so that way the excitation due to this excitation source will be reduced, and you might solve the problem just by moving it forward downstream. Acoustic silencers is another solution that the Energy Institute suggests for the main line excitation. Regarding the mainline response, we can change how the mainline responds to the shell motor vibrations, changing wall thickness. That would change the shell motor vibration, and it might reduce the acoustical excitation because it detunes them from the source of vibration. Removal of circumferential discontinuities. You might say, okay, I'm not gonna put the pressure gouge there, or in the case you have supports, if you're welding them, you said, okay, I'm not gonna weld the supports because there's a probability of failure. So instead of welding them, I'm gonna use special supports that they don't require welding to the main line. And this is avoid the use of welded supports. As I said, you can use special supports. Another solution for the mainline response is the use of circumferential stiffening rings. That will change the shell motor vibration, and it might detune it from the source of vibration. So conclusion. In process plants with large capacity, large sound power generators by pressure relief valves or blowdown valves with restriction devices sometimes result in severe high-frequency piping vibrations. This vibration phenomenon is called AIV, acoustical induced vibration. Energy Institute guidelines offer a screening option based on LOF concept, likelihood of failure, to help minimize the risk of vibration induced fatigue in the process piping. Design options to improve a piping system's strength and integrity in the context of AIV excitation, most focus on points of asymmetric discontinuities. AFT Arrow 10 offers a comprehensive way to apply Energy Institute guidelines directly from the hydraulic model. So this would be the end of my presentations. I hope you liked it. Now we're going to move forward to some questions that you might have. So apparently there's no questions. I know that probably, but if you have any questions now and you want to send it to me, my email is ronaldopinto@aft.com. And if you have any questions, please send it and I'll answer them. Thank you, Jack. So what's next? You will receive a follow-up email with the link to the recorded webinar. We invite you to join us in the upcoming webinars at the Learning Center and the webpage of AFT. You can request an evaluation license to sales@aft.com. Pricing information in US, contact AFT. International, contact your local channel partner. thank you very much for attending. I hope the webinar was interesting for you. And again, if you have any questions or just send me a direct email, or you can send it to webinar, and I'll try to respond to your questions. See you in the next opportunity. Thank you for joining us today.